2. Inferential Statistics. At the end of the previous chapter, we saw how z-scores can be used to find the probability that a random element will have a score above or below a certain value. To do this, the population had to be normally distributed, and both the population mean and the population standard deviation had to be known. Most research, however, involves the opposite kind of problem. Instead of using information about a population to draw conclusions or make predictions about a sample, the researcher usually wants to use the information provided by a sample to draw conclusions about a population. For example, a researcher might want to forecast the results of an election on the basis of an opinion poll, or predict the effectiveness of a new drug for all patients with a particular disease after it has been tested on only a small sample of patients. Statistics and parameters. In such problems, the population mean and standard deviation, mu and sigma, which are sigma or theta, which are called the population parameters, are unknown. All that is known is the sample mean and standard deviation. These are called sample statistics. The task of using a sample to draw conclusions about a population involves going beyond the actual information that is available. In other words, it involves inference. Inferential statistics therefore involve using a statistic to estimate a parameter. However, it is unlikely that a sample will perfectly represent the population it is drawn from. A statistic such as the sample mean will not exactly reflect its corresponding parameter, the population mean. For example, in the study of intelligence, if a sample of 1,000 people is drawn from a population with a mean IQ of 100, it would not be expected that the mean IQ of the sample would be exactly 100. There will be sampling error, which is not an error but just natural expected from random variation, that will cause the sample statistic to differ from the population parameter. Similarly, if a coin is tossed 1,000 times, even if it is perfectly fair, we would not expect to get exactly 500 heads and 500 tails. The random sampling distribution of means. Imagine you have a hat containing 100 cards, numbered from 0 to 99. At random, you take out 5 cards, record the number written on each one, and find the mean of these 5 numbers. Then you put the cards back in the hat and draw another random sample, repeating the same process for about 10 minutes. Do you expect that the means of each of these samples will be exactly the same? Of course not. Because of sampling error, they vary somewhat. If you plot all the means on a frequency distribution, the sample means form a distribution called the random sampling distribution of means. If you actually try this, you will note that the distribution looks pretty much like a normal distribution. If you continue drawing samples and plotting their means ad infinitum, you would find that the distribution actually becomes a normal distribution. This holds true even if the underlying population was not at all normally distributed. In our population of cards and the hat, there is just one card with each number, so the shape of the distribution is actually rectangular, as shown in figure 2.1. Yet its random sampling distribution of mean still tends to be normal. Here we see that figure 2.1, where you have the distribution of population of 100 cards, each marked with a unique number between 0 and 99, showing that it is a rectangular distribution. These principles are stated by the central limit theorem, which states that the random sampling distribution of means will always tend to be normal, irrespective of the shape of the population distribution from which the samples are drawn. Figure 2.2 is a random sampling distribution of means. Even if the underlying population formed a rectangular, skewed, or any other non-normal distribution, the means of all the random samples drawn from it will always tend to form a normal distribution. The theorem further states that the random sampling distribution of means will become closer to normal as the size of the samples increases. So here's the figure that shows the ultimate result of drawing a large number of random samples from a population and plotting each of their individual means on a frequency distribution. According to the theorem, the mean of random sampling distribution of means, symbolized by mu subscript mean, showing that it is the mean of the population of all the sample means, is equal to the mean of the original population. In other words, mu of x is equal to mu. If figure 2.2 were superimposed on figure 2.1, the means would be the same. Like all distributions, the random sampling distribution of means shown in figure 2.2 not only has a mean, but also has a standard deviation. As always, standard deviation is a measure of variability, a measure of the degree to which the elements of the distribution are clustered together or scattered widely apart. This particular standard deviation, the standard deviation of a random sampling distribution of means, is symbolized by, I want to say sigma of the mean, signifying signifying that it is the standard deviation of the population of all the sample means. It has its own name, standard error or standard error of the mean, sometimes abbreviated as SE or SEM. It is a measure of the extent to which the sample means deviate from the true population mean. Figure 2.2 shows the obvious. When repeated random samples are drawn from a population, most of the means of those samples are going to cluster around the original population mean. In the numbers in the hat example, we would expect to find many sample means clustering around 50, say between 40 and 60. Rather fewer sample means would fall between 30 and 40 or between 60 and 70. Far fewer will lie out towards the extreme tails of the distribution between 0 and 20 or between 80 and 99. If the samples each consisted of just two cards, that would happen to the what would happen to the shape of figure 2.2? Clearly, with an n of just 2, there would be quite a high chance of any particular sample mean falling out towards the tails of the distribution, giving a broader, fatter shape to the curve, and hence a higher standard error. On the other hand, if the sample consisted of 25 cards each, it would be very unlikely for many of their means to lie far from the center of the curve. Therefore, there would be a much thinner, narrower curve and a lower standard error. Thus, the shape of the random sampling distribution of means as reflected by its standard error is affected by the size of the samples. In effect, the standard error is equal to the population standard deviation, sigma, divided by the square root of the size of the samples, n. Therefore, the formula for the standard error is sigma mean is equal to sigma divided by, or standard deviation, divided by the number, square root of the size of the samples. Standard error. As the formula shows, the standard error is dependent on the size of the samples. Standard error is inversely related to the square root of the sample size, so that the larger the n becomes, the more closely will the sample means represent the true population mean. This is the mathematical reason why the results of large studies or surveys are more trusted than the results of small ones, a fact that is intuitively obvious. Predicting the probability of drawing samples with a given mean. Because the random sampling distribution of means is by definition normal, the known facts about normal distributions and z-scores can be used to find the probability that a sample will have a mean of above or below a given value, provided, of course, that the sample is a random one. This is a step beyond what was possible in Chapter 1, where we could only predict the probability that one element would have a score above or below a given value. In addition, because The random sampling distribution of means is normal even when the underlying population is not normally distributed. Z-scores can be used to make predictions regardless of the underlying population distribution, provided once again that the sample is random. Using the standard error. The method used to make a prediction about a sample mean is similar to the method used in Chapter 1 to make a prediction about a single element. It involves finding the z-score corresponding to the value of interest. However, instead of calculating the z-score in terms of the number of standard deviations by which a given single element lies above or below the population mean, the z-score is now calculated in terms of the number of standard errors by which a sample mean lies above or below the population mean. Therefore, the previous formula of the z-score equaling mean minus mu over standard deviation now becomes z-score is equal to the mean minus mu over standard errors. For example, in a population with a mean resting heart rate of 70 beats per minute and a standard deviation of 10, the probability that a random sample of 25 people will have a mean heart rate above 75 beats per minute can be determined. The steps are as follows. Firstly, calculate the standard error. So you take the standard deviation of random samples of a mean by taking the standard deviation, dividing it by the sample size, the square root of the sample size, which in this case would be 10 divided by the square root of 25, which is equal to 10 divided by 5 over, which is equal to 2. Calculate the z-score of the sample mean. So z-score is equal to the mean minus the population mean over the standard deviation of random sampling mean. So in this case, the mean was 75. So you subtract that by population, which is 70, and divide that by 2 to get 2.5. Find the proportion of the normal distribution that lies beyond the z-score. Is the next step. So table 1.3 shows that this proportion is 0.0062. Therefore, the probability that a random sample of 25 people from this population will have a mean resting heart rate above 75 beats per minute is 0.0062. Conversely, it is possible to find what random sample mean number, where the population size or sample size is 25, is so high that it would occur in only 5% or less of all samples. In other words, what mean is so high that the probability of obtaining it is 0.05 or less. Table 1.3 shows that the z-score that divides the bottom 95% of the distribution from the top 5% is 1.65. The corresponding heart rate is the population mean mu plus 1.65 times the pop 1.65 times standard errors. As the population mean is 70 and the standard error is 2, the heart rate will be 70 plus 1.65 times 2, equaling 73.3. This figure, 2.3, shows the relevant proportions of the random sampling distribution of means. The appropriate z-score is then plus 1.65, not plus 2, because it refers to the top 0.05 of the distribution, not the top 0.025 and the bottom 0.025 together. Okay, so it is also possible to find the limits between which 95% of all possible random sample means would be expected to fall. As with any normal distribution, 95% of the random sampling distribution of means lies within approximately plus or minus 2 standard errors of the population mean. In other words, within a z-score of plus or minus 2. Therefore, 95% of all possible sample means must lie within approximately plus or minus 2 standard errors of the population mean. As Table 1.3 shows, the exact z-scores that correspond to the middle 95% of any normal distribution are in fact plus minus 1.96, not plus minus 2. The exact limits are therefore 70 plus or minus um, 1.96 times 2, which would be 66.08, and 73.92. Applying this to the distribution of resting heart rate, it is apparent that 95% of all possible random sample means will fall between the limits of mu plus or minus 2 times the standard deviation of random sampling of the means. That is approximately 70 plus 2 times 2, or 66 and 74. Estimating the mean of a population. So far, we have seen how z-scores are used to find the probability that a random sample will have a mean of above or below a given value. It has been shown that 95% of all possible members of the population will lie within approximately plus or minus 2, or more exactly, plus or minus 1.96 standard errors of the population mean, and 95% of all such means will be within plus or minus 2 standard errors of the mean. Confidence limits. The sample mean lies within plus or minus 1.96 standard errors of the population mean of 95% of the time. Conversely, mu lies within plus and minus 1.96 standard errors of the mean 95% of the time. These limits of plus and minus 1.96 standard errors are called confidence limits, and the 95% confidence limits. Finding the confidence limits involves inferential statistics because a sample statistic is being used to estimate a population parameter. For example, if a researcher wishes to find the true mean resting heart rate of a large population, it would be impractical to take the pulse of every person in the population. Instead, he or she would draw a random sample from the population and take the pulse of persons in the sample. As long as the sample is truly random, the researcher can be 95% confident that the true population mean lies within plus or minus 1.96 standard errors of the sample mean. Therefore, if the mean heart rate of the sample is 74 and the standard deviation of the random sample mean is equal to 2, the researcher can be 95% certain that the population mean mu lies within 1.96 standard errors of 74, which is between 74 plus or minus whatever is the product of 1.96 times 2, which would be 70.08 and 77.92. So the best single estimate of the population mean is still the sample mean, which is 74. After all, it is the only piece of actual data on which an estimate can be based. In general, confidence limits are equal to the sample mean plus or minus the z-score obtained from the table for the appropriate level of confidence multiplied by the standard error. And there's a formula where it says confidence limits is equal to the sample mean plus or minus z-score times standard error. So the high yield point to remember here is this. Therefore, 95% confidence limits, which are the ones conventionally used in medical research, are approximately equal to the sample mean plus or minus 2 standard errors. The difference between the upper and lower confidence limits is called the confidence interval, sometimes abbreviated as CI. Researchers obviously want the confidence interval to be as narrow as possible. The formula for confidence limits show that to make the confidence interval narrower for a given level of confidence, such as 95%, the standard error must be made smaller. Standard error is found by the formula of standard deviation divided by uh, the square root of the sample size. Because standard deviation is a population parameter that the researcher cannot change, the only way to reduce standard error is to increase the sample size. And once again, there is a mathematical reason why large studies are trusted more than small ones. Know that the formula for the standard error means that the standard error will decrease only in proportion to the square root of the sample size. Therefore, the width of the confidence interval will decrease in proportion to the square root of the sample size. In other words, to halve the confidence interval, the sample size must be increased fourfold. Hmm. Precision and accuracy. Precision is the degree to which a figure, such as an estimate of a population mean, is immune from random variation. The width of the confidence interval reflects precision. The wider the confidence interval, the less precise the estimate. Because the width of the confidence interval decreases in proportion to the square root of sample size, precision is proportional to the square root of the sample size. Let me read that again. Because the width of the confidence interval decreases in proportion to the square root of sample size, precision is proportional to the square root of sample size. So, to double the precision of an estimate, sample size must be multiplied by 4. To triple precision, sample size must be multiplied by 9. And to quadruple precision, sample size must be multiplied by 16. Increasing the precision of research therefore requires disproportionate increases in sample size. Thus, very precise research is expensive and time consuming. Precision must be distinguished from accuracy, which is the degree to which an estimate is immune from systematic error or bias. A good way to remember the difference between precision and accuracy is to think of a person playing darts, aiming at the bullseye in the center of a dartboard. Figure 2.4a shows how the dartboard looks after a player has thrown 5 darts. Is there much systematic error or bias? No, the darts do not tend to err consistently in any one direction. However, although there is no bias, there is much random variation, as the darts are not clustered together. Hence, the player's aim is unbiased or accurate, but imprecise. It may seem strange to call such a poor player accurate, but the darts are at least centered on the bull's eye on average. The player needs to reduce the random variation in his or her aim rather than aim at a different point. Figure 2.4b shows a different situation. Okay. Is there much systematic error or bias? Certainly, the player consistently throws toward the top of the left of the dartboard, so the aim is biased or inaccurate. Is there much random variation? No. The darts are tightly clustered together, hence relatively immune from random variation. The player's aim is therefore precise. Figure 2.4c shows darts that are not only widely scattered, but also systematically err in one direction. Thus, this player's aim is not immune from either bias or random variation, making it biased, inaccurate, and imprecise. Figure 2.4d shows the ideal both in darts and in inferential statistics. There is no systematic error or significant random variation, so this aim is both accurate, unbiased, and precise. Figure 2.5 shows the same principles in terms of four hypothetical random sampling distributions of means. Each curve shows the result of taking a very large number of samples from the same population and then plotting their means on a frequency distribution. Precision is shown by the narrowness of each curve. As in all frequency distributions, the spread of the distribution around its mean reflects its variability. A very spread out curve has a high variability and a high standard error, and therefore provides an imprecise estimate of the true population mean. Accuracy is shown by the distance between the mean of the random sampling distribution of means and the true population mean. This is analogous to the darts player with an inaccurate aim and a considerable distance between the average position of his or her darts and the bullseye. Distribution A in figure 2.5 is a very spread out random sampling distribution of means. Thus, it provides an imprecise estimate of the true population of mean. However, its mean does coincide with the true population mean, and so it provides an accurate estimate of the true population mean. In other words, the estimate that it provides is not biased, but it is subject to considerable random variation. This is the type of result that would occur if the samples were truly random but small. Distribution B is a narrow distribution, which therefore provides a precise estimate of the true population mean. Due to the low standard error, the width of the confidence interval would be narrower. However, its mean lies a long way from the true population mean, so it will be a biased estimate of the true population mean. This kind of result that is produced by large but biased this is the kind of result that is produced by a large but biased, that is, not truly random samples. Distribution C has the worst of both worlds. It is very spread out, having a high standard error, and would therefore provide an imprecise estimate of the true population mean. Its mean lies a long way from the true population mean. So its estimate is also biased. This would occur if the samples were small and biased. Distribution D is narrow and therefore precise, and its mean lies at the same point as the true population mean, so it is also accurate. This ideal is the kind of distribution that will be obtained from a large and truly random samples. Therefore, to achieve maximum precision and accuracy in inferential statistics, samples should be large and truly random. Estimating the standard error. So far, it has been shown how to determine the probability that a random sample will have a mean that is above or below a certain value, and we have seen how the mean of a sample can be used to estimate the mean of a population from which it was drawn with a known degree of precision and confidence. All this has been done by using z-scores, which express the number of standard errors by which a sample mean lies above or below the true population mean. However, because standard error is found from the formula, standard error is equal to standard deviation divided by the square root of the sample population, we cannot calculate standard error unless we know the standard deviation, the population standard deviation, sigma. In practice, standard deviation will not be known. Researchers hardly ever know the standard deviation of the population, and if they did, they would probably not need to use inferential statistics anyway. As a result, standard error cannot be calculated, and so z-scores cannot be used. However, the standard error can be estimated using data that are available from the sample alone. The resulting statistic is the estimated standard error of the mean, usually called estimated standard error, although confusingly, it is called standard error in many research articles. It is symbolized by S of mean and is found by the formula S of mean is equal to S divided by square root of n, where S is the sample standard deviation as defined by chapter 1. T-scores. The estimated standard error is used to find the statistic t that can be used in place of a z. The t-scores rather than the z-score must be used when making inferences about means that are based on estimates of population parameters such as estimated standard error rather than on the population parameters themselves. The t-scores is sometimes known as student's t's. It is calculated in much the same way as z, but while z was expressed in terms of the number of standard errors by which a sample mean lies above or below the population mean, t is expressed in terms of the number of estimated standard errors by which the sample mean lies above or below the population mean. The formula for t is therefore equal to the mean minus the population mean divided by S sub x. Estimated standard error of the mean. Okay. Compare this formula with the formula we used for z, which was the mean minus the population mean divided by the standard deviation error. Just as the z-score tables give the proportions of normal distribution that lie above and below any given z-score, t-score tables provide the same information for any given t-score. However, there is one difference. While the value of z for any given proportion of the distribution is constant, for example, z-scores of plus or minus 1.96 always delineate the middle 95% of the distribution. The value of t for any given proportion is not constant. It varies according to sample size. When the sample size is large and greater than 100, the values of t and z are similar. But as samples get smaller, t and z scores become increasingly different. Degrees of freedom and t-tables. Table 2.1, this one right here, abbreviated table of t-scores. Table 2.1 is an abbreviated t-score table that shows the value of t corresponding to different areas under the normal distribution for various sample sizes. Sample size n is not stated directly in t-score tables. Instead, the tables express sample size in terms of degrees of freedom. The mathematical concept behind degrees of freedom is complex and not needed for purposes of USMLE or understanding statistics in medicine. For present purposes, degree of freedom can be defined as simply equal to n minus 1. Therefore, to determine the values of t that delineate the central 95% of the sampling distribution of the means based on a sample size of 15, we would look in the table for the appropriate value of t for degrees of freedom equaling 14, 14 being equal to n minus 1. This is sometimes written as T14. Table 2.1 shows that this value is 2.145. There it is. 14 and 0.145. As n becomes larger, 100 or more, the values of t are very close to the corresponding values of z. As the middle column shows, for a degree of freedom of 100, 95% of the distribution falls within t equals to plus or minus 1.984. While for a degree of freedom of infinity, this figure is 1.96, which is the same as the figure for z, seen in table 1.3 earlier. In general, the value of t that divides the central 95% of the distribution from the remaining 5% is in the region of 2, just as it is for z. One and two-tailed tests will be discussed in Chapter 3. As an example of the use of t-scores, we can repeat the earlier task of estimating, with 95% confidence, the true mean resting heart rate of a large population, basing the estimate on a random sample of people drawn from this population. This time we will not make the unrealistic assumption that the standard error is known. As before, a random sample of 15 people is drawn. Their mean heart rate is 74 beats per minute. If we find that the standard deviation of this sample is 8.2, the estimated standard error can be calculated by taking 8.2 and dividing it by the random sample. The square root of 15 comes out to be about 3.87. And that would mean that the estimated standard error is 2.1. So for a sample consisting of 15 people, the t-tables will give an appropriate value of t corresponding to the middle 95% of the distribution for a degree of freedom equaling 14, that is n minus 1. Table 2.1 shows that this value is 2.145. This value is not very different from the ballpark 95% figure for Z, which is 2. The 95% confidence intervals are therefore equal to the sample mean plus or minus t times the estimated standard error. That is the sample mean plus minus t and times estimated standard error, which in this example is 74 plus minus 2.145 times 2.1. Which would be 69.5 and 78.5. The sample mean therefore allows us to estimate that the true mean resting heart rate of this population is 74 beats per minute, and we can be 95% confident that it lies between 69.5 and 78.5. So a high yield point to note is that in general, one can be 95% confident that the true mean of a population lies within approximately plus or minus 2 estimated standard errors of the mean of a random sample drawn from that population.